Hey, what's up YouTube? In today's video, I'm going to talk about creating a plugin for dispatching compute shaders and doing shader work in C++. It's a topic I've been deep diving into lately, so I wanted to make at least one video about it before pausing the channel for the foreseeable future. So, in this video, I'll start from a blank blueprint project and show you how to write all the necessary C++ and shader files to dispatch a simple compute shader that draws a sphere mask around your character into a render target, explaining many things along the way. It's nothing fancy, I know, but it's meant to cover the basics. And there will already be plenty of work to do and plenty of things to talk about as we get there. Now, I'll assume you have Visual Studio set up. If not, please follow the official guide here. I'll personally be using Unreal Engine 5.7.1 installed from the launcher without any additional options enabled, and I'll start from an existing blueprint project. That said, things may differ in your case. You might have enabled options, or you may have compiled Unreal Engine from source, and that's totally fine. It won't be an issue at all. You may also already be working with a C++ project, which is fine as well. Just use common sense to adapt the tutorial to your setup. C++ knowledge isn't strictly required, since you'll be able to copy and paste all the code, but if you want to iterate on this simple example, you'll need to understand what you're doing to some extent. So I'll assume you know just enough C++ that I don't have to start a programming tutorial from scratch. Once this example is implemented, I'll move on to an overview of a more concrete use case. A port of the dual depth system from a previous video to a pure dispatch-based approach. I removed Niagara and blueprints entirely, so I'll go over what I did to make that work. I won't dive into extreme detail, but I'll cover enough to explain the main ideas, some gotchas, things to be aware of, and different possible approaches. Hopefully, by the end of the video, you'll be able to replicate this simple example and have enough context and resources to iterate on it and build your own system. Let's get started. So here I am in a brand new blueprint-based project in ENQUEUE 5.7 installed from the launcher. I'm starting with a blueprint project because I'm assuming that's what most people will be working with when they first get interested in doing C++ work. The first goal here is to convert this blueprint project to a C++ project. To do that, I'm simply going to create a dummy C++ class. Keep in mind that this is a one-way step, it cannot be undone, so you may want to back up your blueprint project beforehand. Also, keep in mind that there are probably better solutions for some of the steps I'm about to perform. I'm not really a developer, so this is definitely outside my comfort zone. Feel free to suggest better workflows in the comments below. Anyway, let's create an actor class, whatever, I'll get rid of it later. Now, this may take a while, but it should generate a Visual Studio project for you. At that point, you'll be prompted to close the editor and open the Visual Studio project to compile it. Ctrl B to compile, and everything should compile correctly. You may see this message here though, and to get rid of it, open that editor.target.cs file and add the suggested include order version parameter. Alternatively, you could use latest for both parameters, which may help prevent similar messages in the future. Compile again, and voila. Once that's done, you can launch the project again and make sure it runs smoothly. Cool. Now, I really love working with plugins. They come with a few constraints, but I love the idea of my code being neatly contained in a small, self-contained package that can be easily shared and doesn't affect any of the project's base code. So that's what I'm going to do, create a blank plugin. I'll give it a name, author, and description, and then let it do its thing. It may take a few seconds. Note that you don't have to go through the editor and this interface to create a plugin. You can simply create the folder and all the necessary files yourself, including the .u plugin file, and then regenerate the project files. However, when you're just getting started, it's quite hard to write those files from scratch, so using this utility is helpful. Visual Studio should ask you to refresh the files. At this point, I'm going to close the editor, then delete the dummy actor class I created to initially convert the project from Blueprint to C++. After that, I'll regenerate the Visual Studio project files once more and make sure nothing broke. It shouldn't have, everything still compiles as expected. Yay! Now, a plugin is made up of modules, and by default, creating a plugin will create a single module with the same name as the plugin. Modules let you further isolate and structure your code, and they also allow you to control when a module is initialized, which is especially relevant when working with compute shaders. So I'm going to create a second module. To do this, I'll be honest, I usually do it manually. I copy and paste the base module folder, rename it, and then rename the files inside accordingly. Then I open the CPP file, the header file, and the build.cs file, and do a search and replace to update the module name. Be careful with this step to make sure it's done correctly. And regenerate the project files one more time. Now, this new module needs to be added to the .u plugin file, so let's do that. The type is still set to runtime, but the loading phase must be post-config init, because this module will register global shaders, and doing so requires a specific loading phase. Let's compile to make sure we haven't made any mistakes. Cool. Speaking of shaders, let's create our shader files. In the plugins directory, create a shaders folder, and inside it a private folder. Then create a .usf file. This stands for Unreal Shader Format. You can also create .ush files, which stand for Unreal Shader Header files. .ush files are typically where you declare structs, utility functions, and other shared code, things you want to reuse across multiple shader files, right? As a side note, there are macros that let you create a .ush file that can be used both as a header for .usf files and for C++ files. This may be handy when you want to declare structs in both C++ and HLSL and ensure they match exactly, but I won't dive into that right now. I'll briefly mention it later in the video, but for now, let's keep things simple. Regenerate the project files and open the .usf file. Hashtag pragma once and hashtag include engine public platform.ush. These are mandatory. You can also include additional .ush files here, whether they are your own or ones provided by the engine. Now, this file is going to contain the code for our compute shader, so we can already write the following: brackets, numthreads, parentheses, numthreads x, all caps, numthreads y, all caps, and 1. Void character dot parentheses uint3 dispatch thread id sv underscore dispatch thread id and curly brackets. Cool. Now, let's step aside for a moment and talk a bit about compute shaders. When working with compute shaders, there are many things to keep in mind. The first one is the thread groups count. The name varies depending on the API though. A thread group is exactly what it sounds like, a group of threads, where a thread is a single execution instance of the shader. The number of threads per group can be tweaked. Most of the time, you'll want to work with a total of 32 or 64 threads per group. The ideal number can depend on the hardware and shader, so make sure to try different group sizes and profile on your target platform. It's uncommon to use fewer than 32 threads per group, because the GPU will usually launch a group of at least 32 or 64 threads anyway. Any unused threads will be inactive, which results in a low metric called occupancy, something we generally try to maximize in GPU programming. You can also use more threads per group if it really makes sense for your use case. That said, there is a limit to how many threads you can use per group, 1024 being the number I usually stumble upon when doing research on that topic. Anyway, to begin with, it's perfectly fine to stick with 64 threads per group. Each thread group has a unique linear index, 0 for the first one, 1 for the second one, and so on. Both thread groups and individual threads can also be uniquely identified using their XYZ indices, or IDs. For example, you're free to dispatch 64 thread groups along a single dimension and do the same with threads. This may work well when your compute shader is iterating over a, say, one-dimensional array, right? In our case, we want to quote-unquote generate a 2D texture, so it makes sense to dispatch thread groups in X and Y, with each group launching threads in X and Y as well. For example, with 64 groups in X and 64 groups in Y, and 8 threads along each axis, giving a total of 64 threads per group, or target, you could iterate over a 2D array, like a texture, that's 512 by 512 pixels. If you're working with a volume texture, it might make sense to use the z-axis as well, right? You could say dispatch 128 groups in X, Y, and Z, each with 4 threads along each axis, still totaling 64 threads per group. This would let you iterate over a 512 by 512 by 512 volume texture. Keep in mind that modern GPUs can launch an insane number of threads. A 128 cube dispatch with 64 threads per group results in pretty much 135 millions of threads. That sounds like too much, but it's not that much for today's hardware, really. Anyway, I mentioned earlier a limit of 1024 threads per group. And when it comes to the number of thread groups, the limit is usually around 65k per dimension, so you can theoretically launch billions of threads. That doesn't mean you should, of course, but when you're starting out, assuming you're working with reasonable texture or array sizes, focus on choosing a sensible number of threads per group and don't worry too much about the group count. Just dispatch as many groups as you need to process all of your data and choose to use the X, Y, and Z dimensions according to the dimension of your data and what makes the most sense. 2 dimensions for 2D textures make sense, right? Also, keep in mind that there's a direct relationship between a thread group's linear index and its XYZ index, or ID. You can manually convert between the two if needed using simple, straightforward formulas. Now, there's one more 3D ID you should be aware of, and it's probably the most useful one. Dispatch thread ID. This represents the thread's overall XYZ ID across the entire dispatch. It's extremely handy, for example, when using it directly as a pixel coordinate to access a 2D texture. All of these values are integers or int3s that you can access inside any compute shader. You can simply pick the ones you're interested in. In practice, dispatch thread ID is the one you'll use most often, especially when getting started with basic compute shader work, like I do. There's a lot to say about compute shaders and GPU programming in general, and I've barely scratched the surface myself. I'm just getting started, so I won't pretend to be an expert. I'm actually making this video and explaining all of this for my own benefit as well. In a way, you are my rubber ducks. And there's no point in already going deep into the black voodoo magic that is GPU programming. But it doesn't hurt to be familiar with a few concepts from the get-go, even though they won't really matter for our particular use case of drawing a simple sphere mask around our character. Thread groups and threads are programming abstractions. They don't directly map one-to-one to physical GPU hardware units, but they do correspond to how the GPU expects work to be organized. Thread groups exist mainly to enable cooperation between threads. First, threads inside a group can share fast on-chip memory, often called shared memory or group shared memory. This is extremely useful for optimizing many algorithms: FFT, tiled matrix multiplication, prefix sums, sorting, and so on. Second, thread groups can synchronize using barriers. This allows you to safely coordinate access to shared memory. And a very common optimization pattern combines both ideas. Instead of every thread loading the same data independently, which may waste bandwidth and hurt performance, a subset of threads loads the data once into shared memory, then the entire group synchronizes before using it. This is of course a simplified explanation. Designing efficient shared memory algorithms is not trivial, but that's the general idea. Now, a thread is a single logical execution of your shader code, and you write your shader as if each thread runs independently. In reality, however, threads do not execute independently, and it would be misleading to think of a GPU thread the same way you think about a CPU thread as a physical on-die entity. On a CPU, you might have, for example, 16 physical cores, which can expose around 32 hardware threads using techniques like SMT. On a GPU, you can't really answer the question, how many threads does this GPU have? Because threads are not physical objects. They are an abstraction. GPUs are made of many specialized execution units: vertex processors, pixel shaders, compute units, CUDA cores, tensor cores, and so on. And these do not map cleanly to a fixed thread count. Because of this, a thread is primarily a programming concept. It defines how much work you dispatch and how your code is written, not how the hardware is physically structured. Dispatched threads are grouped by the GPU into waves, also called warps, wavefronts, or subgroups depending on the API and vendor. A wave typically contains 32 or 64 threads, which is why we often choose dispatch sizes that are multiples of those numbers. A wave is the GPU's real execution unit. All threads in a wave execute the same instruction at the same time in lockstep. A lane is a single thread inside a wave. This is the smallest unit of execution. Each lane processes different data, but follows the same instruction stream as the other lanes in the wave. A lane can be active, meaning it is currently executing instructions, or inactive, meaning it exists in the wave but is temporarily not executing, usually due to control flow, like branching, or because there was not enough work to fully populate the wave. In pixel shaders only, there are two additional concepts. A quad is a group of 4 neighboring lanes corresponding to a 2x2 block of pixels on screen. Quads are used to compute screen space derivatives, such as how UVs vary across pixels, which helps the GPU choose the correct texture MIP level. A helper lane is a special lane created solely to help compute these derivatives. Its output is discarded and never returned to the frame buffer. Because helper lanes are not quote-unquote real visible pixels, most wave intrinsics and UAV access are disabled for them. Now, each lane has its own registers. A register is the fastest and closest storage available to a lane. It's private to that lane, on chip on the GPU die, extremely fast, often single cycle access, but very limited in quantity. Registers typically store local variables, temporary values, loop counters, function parameters, values returned from wave intrinsics, and so on. And because registers are limited, high register usage can reduce how many waves the GPU can run in parallel. So, because all lanes in a wave execute the same instruction at the same time using SIMD execution, GPUs are extremely efficient at data parallel workloads. You know that already. This execution model enables wave intrinsics, which allow threads to cooperate directly at the wave level. These intrinsics are powerful tools for optimization and parallel algorithms, such as reductions, scans, sorting, FFTs, you name it. It's out of the scope of this video, but here are some examples. Anyway, lanes matter because wave intrinsics operate across lanes, and divergence happens between lanes. Divergence is a critical concept in GPU programming. Let's have a look at a simple code example. If different lanes in the same wave disagree on the condition, the GPU executes both paths. Lanes that don't participate in a path are masked out, and the paths are executed serially. This results in a performance cost. So, rule of thumb, divergence within a wave hurts performance, but divergence between thread groups does not. This is why many GPU algorithms are designed around tile-based approaches, unstructured, so that expensive work can be skipped early for entire thread groups. By making decisions at the group level rather than per thread, you avoid divergence inside waves and keep execution coherent and efficient. Yes, GPU programming is an art. So, to summarize very briefly, thread groups organize cooperation. Threads are the programming abstraction, waves define how code actually executes, and lanes are the SIMD elements running in lockstep. Understanding this mental model is key to writing efficient compute shaders. But rest assured, none of this will play a role in today's compute shader example. Still, I'm partly making this video for myself, and digging into these topics was genuinely helpful. GPU programming can feel pretty intimidating at first, so putting clear names on these concepts and understanding the bigger picture can make it a lot less scary. Now that I've fried your brain, let's rewind a bit and focus on what actually matters for our use case. The number of thread groups, which we'll define in C++ later, and the number of threads per group, which we can define here. Unreal Engine lets you define HLSL macros in C++, so conveniently, the number of threads can also be set from C++. That's why I've written this and that in all caps instead of using fixed numbers. These will actually be replaced by numbers by the preprocessor. And I know Z is going to be 1 for this particular use case. We'll be working with 2D arrays, textures, so there's no point in using the Z-axis. The first order of business is to convert the thread ID into UVs. Keep in mind that the thread ID is a unique index across the entire dispatch. So if we dispatch enough threads to, say, compute a 512 by 512 texture, this ID will go from 0 to 511 in each dimension. So we're going to use a constant parameter passed to the shader to tell us the resolution. uint resolution. Next, we compute the texel size, 1 over the resolution as a float. Now we can compute the u-coordinate. We shift the thread id.x index by 0.5 to center it on the texel, then multiply by the texel size. We do the same for the v-coordinate. Next, we need to convert the UVs into world space coordinates to create a mask around our character's location, which is in world space. First, we shift the u-coordinate by 0.5 to center it around the world origin, then multiply it by the scale in x, in centimeters, of the area we want this texture to quote-unquote cover. This will be a float 2 that we pass to the compute shader. Optionally, we can offset the area to center the texture at some arbitrary location. That can be another float 2 passed to the compute shader. We do the same thing for the y-coordinate. Now for the mask itself. First, we create another float 2D to represent our character's location in world space, and a float to describe our sphere mask radius in centimeters. At that point, creating a sphere mask is really easy. It's the inverse of the clamped distance from the texel xy coordinate to the character divided by the radius. Now we need to write this into a texture. So read-write texture 2D, float out texture. When you need to write into a texture, even if you don't read from it, you must use the RW keyword. If you're only reading from it, you can omit it. The type inside the brackets need to accurately match the texture format you're going to use. Here I know I'll only use a single red channel, so float is enough, but typically float4 for RGBA is the most common format for texture 2D. With this in place, you can write values directly into pixels like this. Keep in mind that we can do this because we'll make absolutely sure that the texture is a power of 2 and that we dispatched exactly the right number of thread groups with the right number of threads per group, so the total number of threads matches the texture resolution in each axis. If the texture can be any resolution and non-square, the usual solution is to divide the texture resolution by the number of threads per group and round up to get the number of thread groups to dispatch. That will create more threads than necessary, but that's how GPUs work. In that case, you'll need to check the bounds of the thread ID and early out if it exceeds the texture resolution to prevent out-of-bounds memory writes. Cool. Note that reading a pixel at an integer coordinate works the same way. That said, to sample a texture while accounting for sampler settings like bilinear filtering, addressing modes and so on, you need to create a texture 2D sampler in addition to the texture 2D parameter. You can then use a texture 2D sample function, provide the texture, texture sampler, and UV to sample the texture. Note that these need to be bound in C++, which is what we'll cover next, because at this point our shader is implemented. We should have our spherical mask. Thread ID is converted to UVs, UVs are converted to world positions, and by comparing those world positions to our character position, we can compute a spherical mask with a specific radius. Cool. Alright, time to register the compute shader. What I like to do is create a CPP and header file for each compute shader. This isn't required, it's just my personal preference. Let's use a class wizard for this one. Common classes. Base class is none. Class name, let's say shader underscore character dot. And module is character dot shaders. Cool, let it do its thing. Reload the project, open the CPP and header files, and get rid of this and that. Okay, in the CPP file, I'm going to create a class that derives from FGlobalShader. So class fCharacter.CS, CS for compute shader, public FGlobalShader. And for this to work, I first need to include the CPP file's header, which is already included, good, as well as #include globalshader.h. Next, we are going to use several Unreal Engine macros to register the compute shader and bind its parameters. So declare _exported_shader_type, the name of your global shader class, so fCharacter.cs, global character.shaders_API all caps. That's the name of the plugin module we are working in, suffixed with _API in all caps. Visual Studio should suggest it for you. For this macro to work, you also need #include shader parameter struct. Next macro, shader_use_parameter_struct, fCharacter.cs, again the name of your global shader class, and fGlobalShader. Then we declare the shader parameters struct. Begin _shader_parameter_struct, fParameters, comma, and leave the rest empty, end _shader_parameter_struct. Between these two lines, we list all the constant parameters used in the compute shader. Be extremely careful. Names and types must match exactly. I personally like to temporarily copy-paste them in here. So shader_parameter uint32 resolution, shader parameter f_vector_to_f scale. Note that f_vector_to_f uses floats and matches the HLSL float 2, while f_vector_to_d, which is what you typically use for 2D vector, uses doubles. So again, you have to be a bit careful about matching the exact types. Anyway, f vector to f origin, f vector to f location, and float radius. Binding a texture is slightly different. Shader underscore parameter underscore RDG underscore texture underscore UAV. Read-write texture 2D, float, out texture. So again, if you write to a texture, even if you don't read from it, you must use RW for read-write. And this requires what we call an unordered access view or UAV. If you only read the texture, you'd just use a texture 2D and use a shader resource view or SRV instead. The same principle applies to buffers and structured buffers. Think of arbitrary arrays and so forth. You use the RW keyword plus a UAV for write access, and you use SRV for read-only access. Now, if you need to sample the texture with UVs, pixel interpolation, filtering, and so on, you'd also need shader underscore parameter underscore sampler, sampler state, and the name of the sampler defined in HLSL. At this point, all constants are bound and their types match. Always double or triple check this. Anyway, moving on. FGlobalShader has two public static functions that we can override. The first one, should compile permutation, controls which platforms support this shader. And here I won't be using any fancy shader features, so I suppose SM5 is fine. The second one, modify compilation environment, is quite handy and lets you define HLSL macros from C++. Remember, I used macros to define the number of threads launched per thread group. This is where those values are defined, and I usually expose them as public static variables. Static const uint32 num threads x equal 8, and same for y. Final step, outside of the FGlobalShader class, on its own line, we implement the global shader like this. Implement underscore global underscore shader. FCharacterDotCS is the name of your global shader struct. And here I'm using the name of the module that handles the shader code, / the name of the compute shader file I want to implement, and finally the name of the function I want to call inside that shader file. And its type is compute. Now, this path by itself does not correspond to any real directory. It doesn't exist, right? That's because there are a few very important steps I haven't mentioned yet. In the shaders module's main CPP file, I'll want to #include interfaces /iPluginManager. And in the module startup function, I'll do the following. First, create an fstring public shader dir, and I'll want to combine paths. The base directory of the plugin itself, and the path of our shader file. Oops, let's fix the typo. So character.dot is the name of my plugin, not the module, right? Next, I'm going to add a directory mapping, like so. So this path is going to map to something I called character.shaders/, and that's where this so-called quote-unquote virtual path comes from, okay? Also, stay with me, one more important step. In the shaders module.build.cs file, we need to list a couple of dependencies related to shaders and the rendering pipeline. RHI, RenderCore, and projects. We are not done yet, but at this point, things should at least compile and the project should launch. Cool. Now, it's common practice to create a class with a static function that acts as an interface for a compute shader. Again, there are many ways to achieve the same result. I'm simply showing what I'm used to doing and what works well for me. Feel free to explore Unreal Engine's source code to see the many existing approaches. So in this header, I'm going to create a class. Class CharacterDotShaders_API, all caps, and I usually name this kind of class using the following pattern. F followed by the name of the shader, followed by shader interface. This class is going to expose a single public static void function called addPass_renderThread to emphasize that it must only be called from the render thread. This is common practice in Unreal Engine. And for now, it only takes a reference to the graph builder and a pointer to the global shader map. More on that in a second. So let's implement it. First, it's a good idea to make sure this function is actually executed on the render thread. Ensure is in rendering thread. Second, using the graph builder, we can add debug events. And for this to work, we need the following include. #include renderGraphBuilder.h. I'm also going to include renderGraphUtils because I'll be using utility functions for dispatching compute shaders, which saves a lot of boilerplate code. No need to reinvent the wheel. Next, I need to get a reference to my compute shader class using a shader map reference, like this. Now, all constant inputs are bound through a parameter structure, but at this point, no actual values are being passed to the shader yet. That's what we'll do next. First, allocate the parameters. Then I like to list all the parameters I need to pass. Thanks to the shader parameter macros, autocompletion should work properly and help Visual Studio understand what parameters exist in the shader. These are the arguments that will eventually be passed to this static function. For example, the resolution can be a uint32. The scale can be a const reference to an f vector to f. Origin, same. Location, same. And radius can be a float. Textures and buffers are handled a bit differently, but it's still straightforward. For anything that's an SRV, we ask the graph builder to create an SRV. And for textures, you pass an FRDG texture ref. And for buffers, you pass an FRDG buffer ref. Passing these by value is fine, as far as I know. For UAVs, whether textures or buffers, you simply use create UAV instead of create SRV. That's all there is to it. Voilà. Next, we update the function signature to include all these new parameters. The final step is to compute the number of thread groups to dispatch. So const f int vector group count, and to be safe, we divide and round up the resolution by the number of threads per group, and that in x and y. This gives us the group count needed to dispatch a single execution of the shader that processes every pixel in the texture. Alternatively, we could use this helper function to do pretty much the same thing. FComputeShaderUtils getGroupCount, FComputeShaderUtils golden2D group size. You can see the golden 2D group size is 8, the same value as ours. And it does the same thing as we did, divide and round up. Finally, we use FComputeShaderUtils to add the pass. We provide the graph builder, an RDG_event_name, flags, our compute shader, our parameters, and the group count. Compile, and voila, our compute shader implementation is almost complete. Now we need some kind of interface to initiate the dispatch from the game thread, gather the necessary data, like character allocation, and enqueue a render command on the render thread to call this add_pass function. And once again, there are many ways to do this. I'll show you one of them. One of my favorite things when programming with Unreal Engine in C++ is using subsystems. They are incredibly powerful and very easy to work with. There are several different kinds of subsystems, and I encourage you to look into them if you're not already familiar with the concept. It's a bit outside the scope of this video. In this case, I'll be creating a uLocalPlayer subsystem. These specific subsystems are automatically created whenever a local player is created. And since I want to generate a spherical mask around my character, they are a convenient place to access the character's location and manage a quote-unquote global system that is specific to a single player. I'm going to create a new dummy class, this time in the base module. Name it CharacterDotSubsytem. Reload files, get rid of this, and that we can keep. I'm going to derive from uLocalPlayer subsystem. Get rid of that. Generated body. Now, I don't quite remember which header to include, so let's take a look at the API. It's in the engine module, great, so we should be able to include that header without any issues. Subsystems all come with virtual functions that you can override, some of which are required and some optional. Here I'm interested in the virtual functions defined in the base subsystem class that we may want to override. This one, let's copy it. Override. That one also. Override, and that one. Override. Implement all of them and simply call their superclass implementation. Cool. Now, this subsystem is going to hold a weak reference to a uTextureRenderTarget2D. I'm using a weak pointer because I don't want this subsystem to have any control over the lifetime of the render target. I just want to reference it if it exists and if it's valid. And it looks like we don't even need to include anything or forward declare the type. Okay, so let's compile just to be sure. Whoops. Oh, I'm deriving from a uObject, so I need the uClass macro. Another error. Get rid of that semicolon. And what now? Something about missing headers? Oh right, it's a uClass, so I need to include the generated header. What now? Oh, I'm missing the u prefix. Here we go. Next, I'm going to create a blueprint exposed function to set that render target. So u function blueprint callable, bool set render target, and let's pass a pointer to a uTextureRenderTarget2D. Let's implement it. If the provided render target 2D is valid, we set it and return true, else we return false. Oh, and it looks like I need to include a header after all. Let's have a look at what the API says. It's in the engine module, so I should be able to include this header as is. Compile. Whoops, typo. Yep, all good. Next, let's create a blueprint exposed function to draw the render target. So again, uFunction blueprint callable, bool draw render target. And let's implement it. So the goal here is to capture every data that needs to be sent to the render thread. So these, and enqueue a render command for dispatching the compute shader, right? So I'm first going to do a shit ton of safety checks because I'm nuts. If the render target isn't valid, return false. If the render target width is invalid, return false as well. If the render target is not square, return false as well. And remember, we assumed that the texture uses a single channel. So let's make sure that's actually the case. If the render target format isn't, for example, a 32-bit single channel format, we simply return false. The exact format requirement is somewhat arbitrary here. It could just as well be a 16-bit or 8-bit or even multiple channels. It all depends on your specific use case, right? Next, we retrieve the world and check that it's valid as well. Next, get the local player. From the local player, get the player controller. And from the player controller, get the pawn. Finally, get the pawn's world location. From the render target asset, I'm also going to retrieve the render target resource, so I'll do that here. Now, there are two possible approaches here, I guess. This code runs on the game thread, right? So we can use the game thread specific function to get the render target resource and then capture it to pass along to the render thread. Alternatively, we could capture a pointer to the render target asset itself and retrieve the render target resource directly on the render thread. If you dig into Unreal Engine source code, you'll find many different ways to accomplish the same thing. It can be a bit puzzling at first, but that's just part of the process. You experiment, you make mistakes, and eventually you figure out what works. And I hope this video will be able to provide some guidance. Anyway, where are we now? We have the character location, we have the resolution from the render target, we have the texture, well, kind of. It's a bit more complicated than that, but it's a start. Next, we need the scale, origin, and radius. These values are arbitrary and for the purpose of this tutorial can be set through blueprints. So let's go ahead and create them. F vector to F scale, origin, and float radius. And let's say create a function to set them. Easy peasy. uFunction, blueprint callable, void set draw context, in scale, in origin, in radius. Implement it. Voila. And while we are at it, we might as well make sure they are valid. First, let's check the radius. And check the scale. I'm probably overdoing it with the safety checks, but whatever. Compile, all good, great. Now it's time to capture this data and send it to the render thread. This is done using an enqueue_render_ command. Now I'm going to run a small experiment and create a kind of checkpoint in the video. From here on, the video will branch into 2 chapters. In the next chapter, I'll continue writing the code the same way I have so far. There's very little left to implement, so it will be quite brief. In the chapter after that, I'm going to pretend that I've partially forgotten how the enqueue_render command works. So if you just want to move forward and finish the implementation, watch the next chapter and skip the one after it. On the other hand, if you're new to C++ and think you might learn something by watching me figure things out as I go, skip the next chapter and jump to the one after it. You can use the timestamps to navigate. Alright, see you in a second. First, I'll create an f vector to f containing the pawn's x and y location. So const f vector to f location copy, f vector to f location.x, location.y. Next, I'll create local copies of the scale, const f vector to f, scale copy, scale, the origin, const f vector to f, origin copy equal origin, and the radius, const float radius copy equal radius. These copies are needed for the upcoming enqueue_render command lambda. Next, we can retrieve the RHI feature level from the world. RHI feature level, type feature level equal world scene get feature level. Now comes the enqueue_render command, which will name character dot whatever. inside the lambda, we need to capture everything we want to pass to the render thread. Location copy, scale copy, origin copy, radius copy, resolution, RT resource, and feature level. Next, parentheses, FRHI command list immediate, reference, RHI command list. And this requires the following include. Include RHI command list.h. I'm also going to include rendering thread, render graph builder, shader underscore character dot. And these headers require the following module dependencies: RHI, render core, character.shaders. Now, inside the ENQUEUE render command body, FRDG builder, graph builder, parentheses, RHI command list. Next, FGlobalShader map pointer, global shader map equal get global shader map feature level. As a side note, while digging further into the engine, you'll probably come across Gmax RHI feature level. This is a global value representing the maximum RHI feature level supported by the current platform. So in some cases, instead of capturing and passing around the feature level manually, you might be able to rely on this global instead, assuming its value matches your needs. Anyway, next, FRHI texture pointer, texture RHI equal RT resource get render target texture. FRDG texture ref, RDG texture, graph builder dot register external texture, create render target, texture RHI, text character dot RT, whatever. Oh, I made a small mistake here, so let's fix that. Finally, FCharacterDotShader interface, add pass, render thread, graph builder, global shader map, resolution, scale copy, origin copy, location copy, radius copy, RDG texture. Finally, graph builder.execute. Let's compile. Cool. You can now use the timestamps below to skip the next chapter. Our C++ implementation is pretty much done. All that's left is setting up the project and creating a blueprint to assign the subsystem's render target and call its draw function on tick. So let's pretend I'm partly new to this and have to figure out things on my own. We can do an engine-wide search for the ENQUEUE render command macro. Niagara Data Interface Array Implementation. That looks promising. Let's copy this block. Let's remove everything inside the block and just close it. Good. The name NDI array sim cache write looks arbitrary, so I guess we can rename it to something more meaningful. Next, this is where we define the list of variables we need to capture and pass to the render thread. Proxy render target equals this, so that's a pointer to self, and we don't need that, and the rest we can get rid of as well. Instead, what do we actually need to capture? Oh, right, so the character location, the scale, and here we actually need to create a local copy. Same for the origin, and radius. Then resolution, which is already a local variable, and RT resource. And as for this ENQUEUE render command syntax, let's pretend I have no idea how it works. So time to dig into more examples in the source code to see how others do it. So command list, command list, command list. It looks like it's used everywhere, right? So even though this is empty, it should at least in theory compile. So let's try compiling. It does not. Unresolved externals. When I see that, a few things immediately come to mind. Missing headers, missing plugin or module dependency, and also mismatch between function declaration and definition, amongst other things. Now we can probably discard the last option, since it was compiling fine the last time we made any significant changes to our subsystem class. The error mentions FRHI and related types, so this is definitely tied to the rendering system. So let's check the API for some of these structs. Okay, let's try including this header. Still not compiling. So time to check for missing module dependencies. RHI. We included RHI as a dependency for the shaders module, but not for the base module. But even after that, it's still not compiling. Okay, let's try another struct, like fRenderCommandList. Include the header. Oh, we need another dependency, renderCore. Compile. Great. Next, let's make use of our shader interface static function. First, we need to include it, but remember it's in another module. This means we need to add yet another dependency, our own shaders module. And now we can safely include our own header. Visual Studio still complains though, for some reason. I'm not entirely sure why. It often gets confused by UI's way of doing things. In cases like this, I usually like to just try compiling. See, it fails, but at least it recognizes the function and the class. We are just not passing the arguments correctly yet, so we can move forward. I'm not sure why Visual Studio is complaining here. Typical UI coding experience. Moving on. Now, we need to access the graph builder. Let's do an engine-wide search for FRDG builder. Not particularly helpful. Right, I only have the headers because this UI install doesn't include the full source code. We'll have better luck checking the CPP files on GitHub. Let's try allocate resources, parentheses, with maybe an argument named graph builder. Okay, looks interesting. And where does this graph builder come from? It's passed as another argument. And where is that function called? Scene rendering. Oh, anticlimactic. It's just created from the RHI command list. So we can do the same, I guess. FRDG builder, graph builder, RHI command list. Visual Studio complains. What now? Probably needs a header. Checking the API. Okay, it's in the renderCore module, which we already have as a dependency. So let's just include the header. Yep, good. So obviously this is just for show. This video is fully prepared and scripted, so none of this was a live issue. I'm intentionally making it look like I'm figuring things out in real time to demonstrate how you can get creative and smart with the tools at your disposal. Doing engine-wide searches for functions or structures, consulting the API documentation, and so on. Always check for missing headers and missing module dependencies. Anyway, we are not done yet. Next up, the global shader map. How do we get it? Let's try a different approach this time. Let's use Unreal Engine's assistant. So let's say, how may I get the global shader map in the render thread? Specifically, I'm using the ENQUEUE render command macro to call a function that needs a FGlobalShader pointer. Okay, promising. The assistant suggests something and provides two links that look helpful. Let's check the first link. Blah 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 blah. Get global shader map. Oh, auto. We could use that and let the compiler deduce the type, but I prefer knowing exactly which type we're working with. At least now we know the correct syntax for the feature level. Let's check the second link. Blah blah blah. Blah blah blah. Feature level. it's retrieved from the world. That's pretty handy. What about the global shader map? Oh, T shader map blah blah blah. That's different. These tutorials are probably ancient, and the API has likely changed since then. So which approach is actually correct? Well, this is still interesting, so let's copy that line first. Capture it, and feed it into getGlobalShaderMap. As a side note, while digging further into the engine, you'll probably come across Gmax RHI feature level. This is a global value representing the maximum RHI feature level supported by the current platform. So in some cases, instead of capturing and passing around the feature level manually, you might be able to rely on this global instead, assuming its value matches your needs. Now, for the correct syntax, do we use the tshaderMap thing we see here? Do we go with auto? Or do we stick with what the UI assistant suggested? Well, let's do an engine-wide search. Or maybe just search for the function itself. We've got a pointer here, but we also have a tshaderMap ref here. Well, I see a few examples using the pointer approach, so let's try that. Let's see if it compiles without the @pass function first. Yeah, at least it compiles. Now let's continue and fill in the @pass call with all the arguments, since we already have almost everything we need. What was it again? Oh yeah, resolution, scale, origin, radius. Location before radius. And lastly, the FRDG texture ref. And that we don't have yet. But we currently have a texture resource. And I don't remember exactly how to convert, so let's see if the assistant can help. I have an FTextureRenderTarget resource, and I need an FRDG texture ref. How do I do that? Something about pooled render target. I'm not quite sure what I'm looking at, and to be fair, I was a bit lazy in my original prompt. So I'm going to reiterate and provide a bit more context, just to make sure it understands my intent. Okay. The agent seems quite confident about this getPooledRenderTarget method. Let's give it a shot, I guess. And replay this with our own variable. Blah blah blah, no member named getPooledRenderTarget. Does that even exist? Apparently not. There's no method called getPooledRenderTarget anywhere in the engine. Alright, time to challenge the AI's answer. Okay, it suggests another approach. So replace this with a new method and change this. What does it say? Oh, replace this as well. And that part seems optional, so maybe let's remove it for now. Still, Visual Studio complains. Did I miss something? Apparently not. So let's do an engine-wide search. What's this createRenderTarget method? It outputs a trefCount pointer and expects an FRHI texture, which we do have. And registerExternalTexture asks for a trefCount pointer. The pieces of the puzzle fit, so let's give it a shot. Texture RHI, and let's clean up the rest. What mistake am I making? It asks for a name. And that, I can probably get rid of that. Oh, it's missing a parenthesis. Now get rid of the comments and execute the graph after adding the path. And don't forget to add the FRDG texture ref to the @pass method. Now, I'm really puzzled as to why Visual Studio is still complaining about this, but oh well, let's try compiling. ENQUEUE. Cannot convert from f vector to const f vector to f. Oh, there. Let's create an f vector to f, location copy, location.x, location.y, and capture that instead of the xyz location. Compile again. Yay! What happens if we try it? Let's add a quick UE log macro. Press play, we don't see the log, but that's expected. We haven't set the render target on the subsystem yet, and this draw function isn't called anywhere anyway. So let's create the boilerplate blueprint setup. I'll fast forward through this because it's standard. Create input actions, set up an input mapping context and map the actions, create a player controller and add the input mapping context. Create a character with a spring arm, camera, and maybe a sphere to visualize the location. Implement the look and move inputs. Create a game mode using our player controller and character. Set the game mode in the level and press play. Great, we have our player controller and character and we can move around. Now in the player controller class, we can access the CharacterDotSubsytem. So on begin play, let's set the render target. We need to create one first. Remember, its format must be 32-bit red channel, and we need to enable the support UAV flag. This is because we are creating a UAV, and our pipeline is set up to draw pixels directly into the render target. We could alternatively create a temporary texture 2D, run the compute shader, and copy to the render target, but that's a different approach. Next, set the draw context. Let's say scale is 2.5k centimeters squared. Origin is, 400, radius 500. Next, on tick, call the draw function. Press play. Tada! A sphere mask. Now let's add a plane. Disable collisions. Move it to 400, 400. The mesh size is 100, so scale should be 25 and 25. Let's create a material. Use world position XY, shift by 400, divide by 2500, center the texture, and use that as UVs to sample our texture. Use an unlit emissive material, apply the material, and we are done. Phew, that was quite the journey, right? Now, if you've been following the tutorial along and feel completely overwhelmed or little brain dead at this point, that's perfectly fine. This tutorial wasn't really representative of the actual effort required to get a compute shader working. We deliberately slowed things down, pretending we didn't know anything and working through every little problem. So it dragged on a bit. In reality, it's not that complicated. At the core, you really just need a shader file, an FGlobalShader class to implement the shader, a dummy class to act as an interface, and some kind of game thread class to capture the shader's input data and enqueue a render command. Plus, you need to enable a few dependencies and set the module's loading phase. That said, what if I told you this implementation is wrong? It works, it's mechanically allowed, but not semantically. It violates RDG principles. But what is the RDG again? The official documentation says the render dependency graph, also called render graph or RDG, is an immediate mode application programming interface (API) which records render commands into a graph data structure to be compiled and executed. RDG simplifies high-level rendering code by automating error-prone operations and traverses the graph to optimize memory usage and parallelize render passes on the CPU and GPU. Render dependency graph includes the following features: scheduling of asynchronous compute fences, allocation of transient resources with optimal lifetimes, and memory aliasing, transitioning of sub-resources using split barriers to hide latency and improve overlap on the GPU, blah 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 blah. In other words, it's a powerful beast, a somewhat high-level API designed to take care of a lot of annoying low-level GPU programming details for you. But to do that, it has to guess a lot of things, and it trusts you to use it correctly. RDG is not a full runtime validator. It will allow things that may later break, so having a good grasp of its principles is key. And for now, I still find it very difficult to tame that beast. Sure, the engine source code is the best documentation, but it's filled with extremely complex examples, all with their own quirks. Good luck learning the basics by studying Nanite or Lumen's implementation, right? And you might see RDG being used in ways that aren't optimal for most use cases, but make sense for that one very specific case you just stumbled upon. Then you see this way of doing things, and that way of doing things, and there's the legacy way of doing things, and very quickly it all turns into a very thick fog. Having no background whatsoever in GPU programming, I'm knee-deep into this and still struggling to understand what the red flags are, what the green flags are, and what the most modern way of doing things actually is. RDG really is a beast, but an ever-evolving one, which makes the learning curve even steeper. Add to that the fact that it's likely your first time working with the render thread, having to understand what lives on the game thread, what lives on the render thread, and how to safely pass data between them, and you're in for a wild ride. That's pretty much what I've been doing for the past month. So if you see me making any mistakes, please use the comment section below. I'll make sure to pin your comments. I don't care about being proven wrong, I just want to put out the most up-to-date and accurate information possible. Anyway, getting back to our example, writing directly into the render target is allowed, let's put it that way. As far as I understand it, it's fine for tools, fine for debugging, and even fine for shipping if you rely on RDG purely as a simple scheduler and never rely on its guarantees afterward. In other words, it's fine if you really know what you're doing and are fully in control of everything. And I'm clearly not. Long story short, this apparently isn't bulletproof for many reasons. Throw in async hazards, tiled GPUs, adding another pass that samples the render target later, no aliasing, risky barriers, path reordering, parallel RDG execution, shipping on consoles with stricter drivers, and who knows what else, and you end up with something that seems to work at first, until it randomly doesn't, with the weirdest and hardest to track bugs imaginable. The worst part is that it won't fail deterministically. So yes, RDG will allow you to do things you probably shouldn't. As its name implies, the goal of RDG is to create a dependency graph. That means zooming out, expressing what you're trying to achieve, managing resources, ordering passes, and inserting the necessary safety barriers for GPU reads and writes, memory aliasing, and so on. All in the most optimal way at the cost of a relatively inexpensive graph execution step. And that sounds great, but to do this, RDG has to infer what you're doing from what you give it. And once again, it isn't a full runtime validator, so it won't stop you from wandering into dangerous territory. For instance, register external texture does not forbid UAV writes. If the underlying RHI texture has text create_UAV, either because it was created earlier via RDG with that flag, or because it was specified manually in the render target asset, and your path declares UAV access, RDG will allow it. But as far as I understand it, you should treat any external texture as history, a read-only, pre-existing state that RDG interprets as this texture already exists and I'm consuming it. And even if the shader only writes, RDG cannot treat quote-unquote write-only as safe, because it still doesn't know whether you overwrite all pixels, whether previous contents matter, or whether future passes depend on that previous state. So it must assume this texture already had meaningful data. When you write into it, RDG cannot reason about the previous contents, cannot safely alias or reorder, and cannot validate correctness. The golden rule is simple. If RDG didn't create it, RDG doesn't own it and assumes it existed before the graph. So, imported textures equal history, created textures equal outputs. Mixing the two breaks lifetime and barrier guarantees. Now, if at this point this sounds way too complicated and you're ready to give up, don't. Because fixing our code takes as little as 3 extra lines. First, we create a texture description for a 2D texture. FRDG texture desk, create 2D, provide the resolution, the format, its clear value, and flags important. Next, using the texture description, we ask the graph builder to create a texture. And that gives us an FRDG texture ref, exactly what we had before with the register external texture method. We then let our compute shader write into this RDG created texture. And finally, we add a CopyTexturePass. With this setup, our created texture is the output of the shader. But what about the imported texture? To copy into a texture, it surely needs write access, right? So isn't it technically still an output? Okay, bear with me. Add a CopyTexturePass is not quote-unquote writing to an external texture in the same sense as a compute shader writing via a UAV. It is a well-defined, side-effect-free transfer operation with explicit read-write semantics that RDG fully understands and can reason about. Your shader UAV write is arbitrary code with arbitrary access patterns, potential partial writes, and unknown coverage. And RDG must treat those very differently. Internally, add CopyTexturePass creates an RDG pass roughly equivalent to this. And RDG knows exactly what this pass does. The source is read-only, the destination is fully overwritten, and that matters a lot. There are no conditionals, no partial writes, and no UAV hazards. This is gold for RDG. Because the semantics are known, it can generate perfect barriers. And this is allowed for external textures because the copy is declarative, what happens is known, atomic, one logical operation, side effect free, no hidden reads, and stateless, no dependency on previous contents. So RDG doesn't care who owns the destination, only that the operation is safe. Contrast with your compute shader UAV write, RDG has no idea which pixels you write, whether all pixels are written, whether you read from output first, whether execution is divergent, or whether future passes rely on previous contents. That being said, my first instinct when I learned about the CopyTexturePass was, what about the cost? In almost all real-world cases, the copy is cheap, often effectively free, and far cheaper than the bugs you avoid. Directly drawing into the render target feels optimal, but in modern UE with RDG, the extra copy is usually bandwidth bound, patched, overlapped, sometimes even elided by the driver, and very, very rarely the bottleneck. It's a pure GPU copy with no CPU involvement. Add CopyTexturePass turns into a simple RHI command list.copyTexture or a platform-native blit. No shader execution, no thread synchronization, no CPU stalls. This is peak GPU efficiency territory. Now let's do a quick reality check with some bandwidth math. Say we have a 1024 by 1024 texture, red channel 32 bits, so 4 bytes per pixel, and 1 copy per frame. That's roughly 4 megabytes per frame, and at 60 FPS, that's about 240 megabytes per second. Modern GPUs push hundreds of gigabytes per second. You're spending around 0.1% of available bandwidth. On top of that, copies pipeline extremely well. They don't block ALUs, don't block texture units, are easy to overlap with compute or raster work, and often run on dedicated copy engines on consoles and modern PCs. Your compute shader is almost certainly way more expensive than the copy. There are also important RDG wins you only get because you allow the copy. RDG can reuse the memory of your temporary texture for other passes, other views, or even other systems. If you write directly into an external render target, RDG must treat it as untouchable, no aliasing, higher overall memory pressure. So ironically, the quote-unquote no copy path can be slower globally. With RDG create, write, copy, output, RDG can reorder work, overlap passes, fuse barriers, and move work across queues. With import, write directly, RDG has to be conservative. Now, I guess there are cases where avoiding the copy can be justified. Very large textures, 4K, 8K, many copies per frame, mobile or low bandwidth GPUs, being already bandwidth bound, or passes that run many times per frame like tiles or cascades. In those cases, manual external ownership, raw RHI usage, or long-lived ping-pong render targets can make sense. But those are deliberate performance decisions, not defaults. Pay the copy unless a profiler proves it's a problem. That's why you see RDG temporary textures everywhere, copy passes everywhere, and very few paths that write directly into imported render targets, even in hot systems like GAA, Lumen, Nanite, or Shadow History. They still ping-pong and copy because correctness scales better than micro-optimizations. To sum it up, think of the copy as the price of determinism. You're buying correct barriers, async safety, aliasing, debugability, and resilience for future engine changes for a cost that's usually lost in the noise. Skipping the copy is prematurely optimizing something GPUs are absurdly good at. Regardless of correctness, using a render target to draw directly into it can become very limiting once you start building more complex compute shaders. For example, in this FFT Ocean setup, I really only care about the normals and displacement render targets. But computing this effect requires many more buffers and textures that I don't want to expose as render target assets. On top of that, some of these buffers, like the FFT butterfly lookup table or the base spectrum, only need to be computed once and then hold pre-computed data for the rest of their lifetime. That's why I want to dive deeper into render graph resource management and how to create textures that live only inside the render graph with an extended lifetime. And to illustrate this, I'm going to iterate on this spherical mask example. I want to create a persistent effect like this, where the result from the previous frame is blurred and gradually faded out. Now, why would we technically need another resource for this? We already have a UAV that allows both read and write access to this render target. So in theory, we could read the render target's current value in a compute shader, sample neighboring pixels to perform the blur, fade it out, and then, in that same compute shader, compute the new sphere mask, composite everything together, and write out the new value, right? Well, no, not really. This would cause issues because of race conditions. Remember, we are launching many thread groups, each with many threads. Everything is heavily parallelized, so the exact time at which a pixel is read or written is unpredictable. We might end up writing a new value to a pixel before a neighboring pixel has had the chance to sample it for the blur, which would completely mess things up. Some pixels might read new values, others the old values. That's why ping-ponging between two buffers, one used exclusively for reading and one for writing, is really common. In that case, you do need more than one texture, but it feels pointless to create actual render target assets just for an internal ping-pong system, right? And that's where the render graph comes in. It can create internal textures and buffers for you. Now, if you need a texture or buffer resource to persist across frames, I've identified two approaches. I'll call one the pre-allocated approach and the other the extraction approach. The extraction approach says, render graph, create this resource for me, and then hand me ownership when you're done. The pre-allocated approach is more explicit about ownership. You're saying, I own this resource, and the render graph can borrow it temporarily. Personally, I think the pre-allocated approach offers a clearer mental model and might even be a bit easier to implement. But I'll show both, because you'll encounter both patterns in Unreal Engine, and probably some other variations too. I'm still fairly new to this myself, so I'm learning as I go and teaching at the same time. Not ideal, but that's how it goes. Let's first focus on the changes that are common to both approaches, and I'll fast forward a bit through this part. I no longer have a single shader, but two, an init shader and an update shader. The init shader is actually the one we implemented previously. It draws a sphere mask just like before and was simply renamed. As a result, the C++ and header files containing the shader interface were also renamed, but nothing else really changed. Following this same file structure, a second shader was created, called update. The same principle applies. The header declares the shader interface struct and exposes a single public static function used to add a compute path. The implementation lives in the CPP file, just like before, and it's also declared as an FGlobalShader. The key difference now is that this shader has a previous texture SRV for read-only access and an out texture UAV for writing. Because of that, the static function now takes two FRDG texture refs instead of one and creates the corresponding SRV and UAV. The shader itself is partially similar to the previous one since it still draws the sphere mask, but now it combines it with a blurred result from the previous frame. That's the extra bit. It may look complex, but it really isn't. I simply load the pixel values from 4 neighboring pixels, wrapping the coordinates to make sure I don't go out of bounds. These 4 samples from the previous texture are averaged to produce a blurred value, which is then faded out. The final value is the max between this new sphere mask and the previous mask after blur and fade. Now, in the subsystem, we can get rid of this part for now. It no longer exists. We still need to register our user-provided render target asset with the render graph, because regardless of how we handle temporary resources or compute the effect internally, the result still needs to be written out to that render target. So that part stays. Also, the header was updated to include both shader interfaces. Now, in the subsystem header, inside the subsystem class, I'm going to create a float for the fade amount. Float, fade amount, let's say 0.99. I'm also going to create a blueprint exposed function to set the fade amount. Why not? U function, blueprint callable, void set fade amount, float in fade amount. Let's implement it. Fade amount equal clamp in fade amount 0, 1. Good. From this point on, we have two possible approaches, resource pre-allocation or resource extraction. Let's focus on the extraction approach first. First things first, I'm going to create a trefCount pointer, which is a smart pointer to an object that implements addRef and release, and that object is iPulled_renderTarget. I'm going to call it persistent RT. I'll also want to track the user-provided render target resolution, int32 cached resolution equals 0. Finally, I'll need a function to reset the persistent resources. Void reset persistent resources. Let's implement it. If the persistent render target is valid, we create a local copy and add +1 to the counter. Next, we clear it, removing 1 from the counter, and then we enqueue a render command to safely release it. Its count will then be 0, and it will be garbage collected. By the way, the enqueue render command needs to be mutable, because if not, by default, captured variables are const, and since the safe release method modifies the trefCount pointer, we need the mutable keyword. Upon subsystem deinitialization, I want to release this pooled render target. Now, I am unsure if we do need to flush render commands here, but I'm pretty sure it's safe to do so in this case, so why not? Also, if the user provides us with a new render target, we need to release the old one. Next, in the drawRenderTarget function, I'm going to keep track of the user-provided render target resolution and compare it with our cached value. If they differ, we need to call this reset function and update the cached resolution. Next, we'll need to capture the fade amount. Const float fade amount copy equal fade amount. Capture it. Next, we check if the pooled render target is valid and store the result in a local boolean. Capture it. And I'll need to pass a pointer to the trefCount pointer. And capture it. In the enqueue render command lambda, I'm going to create an FRDG texture description for our output. FRDG texture desc, create 2D, resolution, format, clear value, and flags. With which we ask the graph builder to create a texture. FRDG texture ref, graph builder create texture, our description, and some text, whatever. Next, if our pooled render target isn't valid yet, it means we need to run the initialization pass. To do that, we dispatch the appropriate compute shader through our fCharacterDotInitShader interface, passing in the required list of arguments, and we write the results into the texture we created with RDG. Else, we register the texture that was extracted from the graph the previous frame, so FRDG texture ref, previous RDG texture, graph builder, register external texture, pointer to our persistent render target pointer, and some text, whatever. That's our history, right? Next, we dispatch the update compute shader through our fCharacterDotUpdateShader interface, passing in the required list of arguments. This time, we read from our history and write the results into the texture we created with RDG. And finally, we copy the result to the user-provided render target and queue extraction for the next frame. Let's compile. Okay, great. Run the editor. Play. Awesome, everything works. To summarize, first we register the user-provided render target with the render graph. Then we create our internal output texture using RDG. If this RDG created texture hasn't yet been extracted to persist in our pooled render target, or if it was released due to a resolution change or a similar event, we start fresh and dispatch the initialization pass, writing into the output texture for the first time. Otherwise, we register the previously extracted RDG texture, stored in the trefCount pointer pooled render target and captured in the enqueue render command lambda, with the render graph. We then dispatch the update pass, reading from that pooled render target and writing into the new output texture. Finally, we copy the output texture to the user-provided render target and extract the RDG created texture for storage in our trefCount pointer. On the next frame, this texture will be valid. Initialization will already have occurred, so from that point on, only the update pass will be dispatched. Keep in mind that extraction must happen every frame. each frame we create a new RDG texture and extract it for storage in our trefCount pointer. And there you have it. That's one way to approach this problem. Now let's take a look at the pre-allocation method. So here I'm back to where I was before implementing the extraction approach, right? I have my two compute shaders that I need to call, and I need to pass the persistent textures to them. First things first, I'll need a trefCount pointer to an I-pooled render target. Next, I'll need a function to ensure our resources are pre-allocated. Now, I could do things differently here. I could add such a function to this subsystem class. This would, however, require capturing this in the ENQUEUE render command lambda, so we can call this do something on the render thread. But I think that can be quote-unquote dangerous. The subsystem might be destroyed on the game thread, and this could become a dangling pointer, causing a crash. Another option you may see in the engine is capturing a weak pointer to this instead. You create it like so. Weak object pointer, you CharacterDotSubsytem, weak this. Capture it, and create a strong pointer using auto if you're lazy. If auto pointer strong this, weak this, get, and then we could call our function. This is safer, I think. But the get method of a weak object pointer and uObject access are not thread safe, so that could introduce race conditions. I don't think that would be an issue in our case, but I'm still fairly new to multi-threading, so please correct me if I'm wrong. Another option would be to make this function static, so you could avoid capturing this and call the function on the render thread like this. That said, here I think the better approach is to use an anonymous namespace. It gives everything inside it internal linkage, meaning the symbols are only visible within that C++ file. It's the modern C++ equivalent of declaring something static. It prevents ODR, one definition rule violations, if another CPP has a function with the same name. In a way, it signals this is an implementation detail, not public API. And the compiler knows it can't be called externally, which opens up better optimization opportunities, at least on paper. It also makes thread boundaries crystal clear, prevents accidental access to game thread members, eliminates the entire this lifetime problem, and is self-documenting. This function operates on these specific pieces of data. So that's what I'm going to do. In the CPP file, I'm going to create an anonymous namespace, and inside it a function called ensure persistent resources. A new render target resolution will need to invalidate existing resources, and I'll need to pass a reference to a trefCount pointer of I-pooled render target. Let's implement it. Our first goal is to decide whether we need to allocate a new resource. So first, if the pooled render target is invalid, we need a new allocation for sure. Next, if the pooled render target is valid, we still need to check its resolution. If it differs, we need a new allocation. So if we do need a new allocation, we release the old resource if it exists. Next, we create a render target description, create 2D disk, resolution, format, clear value, some flags, and some more flags. And using this neat utility function provided by this header, render target pool, we allocate a resource from the render target pool. Render target pool, find free element, f_arrowchild command list immediate, get. We provide the description and our trefCount pointer and some text, whatever. And we return true if a new resource was allocated. I'll also need a function to release the persistent resources. Should be resource singular in this case, but whatever. If valid, create a local copy. Reset the initial trefCount pointer, and ENQUEUE a render command to release the copy on the render thread. Next, in the ENQUEUE render command, we call this function before doing any rendering. Const bool b resource was allocated, ensure persistent resources, blah blah blah. And this needs a reference to a trefCount pointer, so we are going to capture persistent RT by pointer so the render thread can access it. Capture it. And we also now need to capture the fade amount. We then register our newly created pooled render target, FRDG texture ref, persistent RDG texture, graph builder, register external texture, persistent RT pointer, and some text. Next, if it's the first frame or after reallocation, we are going to call the init shader and draw into the newly created pooled render target instead of the user-provided render target. And we simply copy the pooled render target to the user-provided render target. Again, this goes back to the idea of treating registered external resources as history rather than as outputs. Technically, we could write directly to the render target if it's created with UAV access enabled. However, from what I've gathered, it's generally better to use RDG-created textures for outputs and then perform a copy pass for export. This is something I've had trouble confirming on my own, so take it with a grain of salt. Anyway, else we use RDG to create yet another output texture 2D. So desk, create 2D, blah blah blah. Graph builder, create texture, blah blah blah. We call the update shader and provide the persistent render target to read from. That's our history. And the newly created RDG texture to write into. That's our output. Once that's done, we copy the result back to the persistent texture for next frame. And we also add a copy pass to export it to the user-provided render target. This definitely feels suboptimal. We can probably skip the copy passes here. But for now, I'm more or less following my own understanding of RDG, which again could be flawed. Anyway, finally, we execute the graph builder, always. We are not done yet though. We are now tracking persistent resources, so we need to destroy them when relevant. First, upon subsystem deinitialization, I'm gonna call release persistent resources. And we also do that when the user sets the render target. Voilà, compile, run, play, ta-da! Yeah, well, sorry about that, but this isn't exactly bulletproof. All you have to do is change the render target at some arbitrary point after it's been set, and crash. Oops! So again, I really can't emphasize enough how bad I am at GPU programming. And I'm even worse when it comes to understanding multi-threading paradigms and anticipating race conditions and things like that. Checking whether a UObject is valid doesn't actually guarantee that it will remain valid. It might be valid when the if condition is evaluated, but no longer be valid inside the if block itself, because a parallel thread could have destroyed the underlying resource. And I suspect that's what's happening here. Unfortunately, I was kind of stuck and had to ask Claude for some guidance. First, wrap the trefCount pointer in a thread-safe tshared pointer. Second, remove this method. It's no longer called during deinitialization or when setting the render target. Instead, during deinitialization, similar to what we were doing before, create a copy of the tshared pointer, reset the original pointer, and capture the copy so the resource can be released on the render thread. Next, when setting the render target, create a local copy of the tshared pointer. Create an empty holder and capture the copy so it can be released on the render thread. Finally, capture a copy of the tshared pointer instead of a pointer to the trefCount pointer. It's a bit puzzling, I know, but next update those two functions to use the captured shared pointer. And this works. Unfortunately, this video really humbled me. I tried to tackle a subject that's clearly beyond my current skill level, and I'm still trying to fully wrap my head around what's going on. It all comes back to how difficult RDG can be to learn, especially if you don't have a strong programming background. It's an entire API to learn, and one that's designed to operate in a multi-threaded environment. So you have to understand that as well. It's not easy, at least not for me. Anyway, moving on. So hopefully, having implemented both approaches, you now have the mental model in mind. With the pre-allocated approach, you say, hey, let's first create the resource that we need and own, and tell the render graph to borrow it temporarily. With the extraction approach, you say, hey, let's ask the render graph to create this resource for me, and then we receive ownership when it's done. As far as I know, same but different. Pick whichever method fries your brain the least. Here are a few more pointers to help you get more comfortable with compute shaders. This video is only the tip of the iceberg. There's obviously a lot more to cover, but let's focus on the most important things for today. Working with a texture 2D is great, but it can be limiting. It's designed to be thought of as a 2D array, and its format options are restricted. For more general purposes, arrays are often preferred. Several options are available, each with its own use case, and the first deciding factor is whether the array size is known at compile time or not. What does that mean? Quite literally, the array size is hard-coded to be, say, 3, and it's never going to change. In other words, it's known at the time the code is compiled. For this kind of array, assuming you're working with a reasonable size, here's the workflow. Let's say we want a list of 8 coefficients, each holding 4 floats. In HLSL, you'd write this: float 4 coefficients, brackets 8. In C++, between the begin and end macros, you'd add a shader parameter array macro like this: shader parameter array f vector for f coefficients, brackets 8. And you'd set the values when setting the parameters, for instance using a for loop. The same principle applies to fixed size arrays of inline structs. You add the struct keyword, shader parameter struct array, say fLightData, brackets 4. And prior to this, you define a reusable substruct. Begin shader parameter struct fLightData, shader parameter f vector 3f position, shader parameter f vector 3f color, shader parameter float intensity, and shader parameter struct. You do the same in HLSL, struct fLightData, float 3 position, float 3 color, float intensity. That way you can create a fixed size array, fLightData lights brackets 4. Then you'd set this array when assigning parameters, in a for loop or manually. Params light brackets I dot position equal blah 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 dot color equal blah blah blah, and so on. You could also use just a single struct. Get rid of the array keyword and the array size, so shader parameter struct fLightData light. Here we wouldn't need the for loop anymore, right? And in HLSL, you'd get rid of the array syntax. There's a lot to say about structs, but I'll come back to that in a minute. Let's stick to arrays for now. So that's for fixed size arrays. If your array can vary in size, whether every frame or sporadically, this isn't the way to go. Although if the array size is fixed but huge, that may not be the best approach either. There are 3 main options: buffer, structured buffer, and byte address buffer. A buffer is similar in principle to a texture, but one-dimensional. It has a format that dictates its layout in memory, and its template type must fit into 4 32-bit components. Buffers are more commonly used in vertex and pixel shaders, as far as I know. For compute shaders, structured buffer is usually the preferred choice. A structured buffer is templated on a struct. Unlike buffer, the template itself defines the memory layout, and no implicit format conversions occur. It doesn't have a format per se and can hold pretty much anything. A single float, a float 4, an integer, or a custom struct. More on that in a second. Finally, a byte address buffer is a very generic, low-level buffer that stores data in 4-byte chunks, effectively as uint32 values. Converting to floats on reads requires as float, and converting from floats on writes requires as uint. In most driver implementations, these conversions are effectively no ops, so there's no performance impact. I'll focus on structured buffer since it's what you're most likely to encounter. Once you understand how to work with it, using the other 2 buffer types is relatively straightforward. In HLSL, you declare a structured buffer like so. Read-write structured buffer, and for read-only, structured buffer, type, and name. In C++, you then construct the shader parameters like so. Shader parameter RDG buffer, UAV, read-write structured buffer, type, name. And shader parameter RDG buffer SRV, structured buffer for read-only, type, and name. Keep in mind, you need to respect the convention for reads and writes, SRV or UAV, and the RW keyword. If you only read from a buffer, prefer using an SRV for optimal theoretical performance. Anyway, you pass parameters by creating an SRV or UAV as needed. So params, name, graph builder, create UAV or SRV, buffer ref. The buffer ref is an FRDG buffer variable. And for read-only structured buffers, you create an SRV. The buffer ref is an FRDG buffer ref that you can create like so. FRDG buffer ref equal graph builder, create buffer, FRDG buffer desk, create structured desk, the size in bytes of a single element. Here is the size of our struct, flight data, the number of entries in the buffer, and some text, whatever. You also need to fill the buffer with your data held in memory on the CPU side, and that's done using QBufferUpload. GraphBuilder.QBufferUpload, the FRDG buffer ref variable, the actual array data, the size of a single entry multiplied by the number of entries. And that has to be done before creating the SRV or UAV for the structured buffer. Finally, you access a structured buffer in HLSL like so, using brackets to specify the linear index of the entry you want to read. Same for writes, easy peasy. Now, about structs, watch out for something called memory alignment. For example, consider these 2 structs. They are identical in appearances at least, right? 2 float 3 and a float 4. Thus, you might think the struct's size is 40 bytes, 10 floats of 32 bits. But due to alignment rules, as far as I know, the compiler pads the struct so its size is divisible by the largest element. In this case, the float 4, so the struct is 16-byte aligned and ends up being 48 bytes. And there can also be differences in alignment and padding rules between C++ and what the C++ compiler does, and HLSL and what the shader compiler does. This is a whole topic on its own, so we won't go too deep here. And it's not like I'm going to pretend I'm an expert on this anyway. I used an HLSL struct for the first time the other day and got totally owned like the noob that I am. Anyway, you can use structs, but you have to be careful about this. In short, you have a few options. Use macros in C++ to control how and where padding is applied. Again, I'm no expert, so I don't know much about this. Add padding manually to ensure proper alignment. Or, more generally, prefer using float 4 instead of float 3 and assume that 16-byte alignment is a strict requirement. I believe Unreal Engine's macros are specifically designed to handle alignment and related layout concerns, but it can still become an issue. I learned that the hard way when using this struct inside a structured buffer. Alignment beat me there, so definitely keep an eye on that. On a related note, you'll often need the exact same struct definition in 2 places. In C++ to fill buffers, validate sizes, and bind resources, and in HLSL to interpret that memory correctly on the GPU. Duplicating the struct in a .h file and again in a .usf or .ush file technically works, but it's fragile. Sooner or later, someone will add a field on one side and forget to update the other. That's how subtle bugs creep in. Ideally, you want a single source of truth, no duplicated definitions. Unreal Engine supports this through dual-use headers using __C++ guards. C++ compilers define __C++ and HLSL compilers do not. For example, consider this .ush file. Pragma wants ifdef C++, namespace, blah blah blah, struct, ifdef C++, namespace, using blah blah blah, and if. From the HLSL side, the compiler effectively sees this. And from the C++ side, it sees this. In C++, you get a properly scoped type inside UE HLSL, plus a convenient alias, fmydata, for everyday use. The important constraint is that this shared header must be quote-unquote HLSL clean. HLSL has no idea what Unreal-specific C++ types are. That's why shared shader structs avoid things like TRA, fvector, uint32, or anything not guaranteed to exist in both languages. The UE HLSL namespace also prevents simple pollution on the C++ side. Without it, every shared GPU struct would end up in the global namespace, which would quickly become unmanageable at Unreal scale. The namespace communicates intent. This type primarily exists to mirror an HLSL definition. The optional alias gives you short names at call sites and potentially allows for future refactors without breaking APIs. In short, this is an HLSL first data layout made just legal enough for C++. It's not something I personally use yet, but I probably should. I actually stumbled upon a C++ file in Unreal's source code that referenced a struct I couldn't find anywhere in the C++ headers, which was confusing at first, until I realized it was coming from one of these shared HLSL headers. So I figured it was worth mentioning. I want to show you one more trick, getting rid of render target assets. It's not something I would always recommend, because it's very powerful, and with great power comes great responsibility. And to be honest, I'm not entirely sure yet what all of those responsibilities are. There may be performance implications I'm not fully aware of, and other caveats as well. But anyway. The idea is to use a render graph internal resource and expose it to all shaders through uniform buffers. A uniform buffer is, as the name suggests, a buffer limited in size that is used to send general-purpose data to shaders. Think of things like view parameters, camera position, and so on. Unreal Engine has a global uniform buffer that is sent to all shaders, and we can extend it via a plugin. And we can do this using a FSceneViewExtension. I'll fast forward through this part because the video is already long enough, and there's not much value in showing the actual coding process. In the shaders module, I created a CPP and a header file for the uniform buffer. The header is fairly minimal and declares a shader struct, as we are used to doing. It contains a texture 2D, a texture sampler, as well as an origin and an inverse scale. It also introduces an important macro we haven't seen before. Declare scene UB struct. This is the name of the shader struct, and this is the name we'll use to access this uniform buffer struct in HLSL across all shaders. The CPP file is just as minimal and implements the uniform buffer struct using another macro, implement scene UB struct. Because of this, I'm fairly certain the code needs to live in a module with this specific loading phase, which is why I added it to the shaders module. That's also why I migrated all the related classes into this module. At this point, everything was referencing everything else, leading to circular dependencies between modules. The simplest fix, when possible, is to consolidate everything into a single module. To do that, I manually copied the files and regenerated the project files. Moving files to a new module usually requires updating the API macros here and there, but otherwise it should be a smooth process. The implement macro is similar to the declare one. It takes the shader struct name, the name used to access it in HLSL, and the name of a static void function that provides default values for the uniform buffer struct. In my case, I create an SRV using a dummy texture, a sampler with default settings, and default values for the origin and scale. Keep in mind that this name is what you'll use to access the struct data in any UE shader written in HLSL. Since it's a scene uniform buffer, you access it using scene.structName.parameterName. You can also define macros in HLSL for easier access. In my case, I created a .usf file containing a simple utility function that converts a world position to UVs for sampling the texture. Then, inside a material using a custom node, I can include this .usf file and simply call my function. And this allows me to replace all those material nodes and render target asset with a single function call. For this to work though, there's a bit more to set up. And that's where the FSceneViewExtension comes in. Still in the shaders module, I created a CPP and header file for the view extension. The header declares a class deriving from FSceneViewExtensionBase. This base class provides a number of useful functions that can be overridden. It also stores a weak pointer to my subsystem, which I initialize in the constructor. This will make sense in a moment. The header also declares a struct used to store the data required on the render thread. Previously, we used ENQUEUE render command lambdas to capture variables. Now we manage that ourselves using a dedicated struct. Thus, the FSceneViewExtension holds this render thread data struct, as well as a trefcount pointer to an iPool render target, which replaces our previous external render target asset. In the CPP file, I set the owning subsystem in the constructor. In the destructor, I safely release the pooled render target. Next, in onBeginViewFamily, which runs on the game thread, I retrieve the subsystem and gather the necessary data, pawn position and so on. This data is stored in the struct I just mentioned, so it can be safely consumed on the render thread. That consumption happens in pre-renderViewFamily_render thread, which essentially replaces our old ENQUEUE render command lambda. This function is automatically called by the engine every frame on the render thread and provides a graph builder, allowing us to do what we previously did inside the ENQUEUE lambda. So this part should look familiar. We create 2D textures, call addPath, and so on. Now the render target resolution is no longer controlled by the user editable render target asset. Instead, it's driven by a parameter set through a blueprint_exposed function. If the resolution changes, we release it to recreate it as the correct size. Other than that, the logic is nearly identical. The only difference is that we don't call graphBuilder.execute because the SceneView extensions handle that internally. What's new, however, is where we set up our uniform buffer struct. I fill in its fields with the correct values. We create an SRV from our internal output texture. No more user-provided render target asset. That's the whole point. Then we set the sampler as well as the origin and inverse scale used to construct UVs. Next, from the scene renderer specific to the SceneView extension, we retrieve the scene uniforms and assign our parameters. If anything goes wrong, I believe it's still necessary to set valid uniform buffer values, though I'm not entirely sure. Just to be safe, I implemented a small helper function that assigns default values in case of invalid pointers before an early exit. Also, this part is optional, but I thought it was worth showing. We can send the data back to the game thread using an async task. This is useful for debugging render thread data. In my case, I simply draw a debug box to verify that the origin and inverse scale values gathered on the render thread are correct. At this point, the only remaining task is managing the lifetime of the SceneView extension. I handle this using a subsystem just like before. The subsystem is now quite bare bones. It no longer enqueues a render command and no longer holds a reference to a texture render target 2D, so there's no longer a blueprint function for passing one in. Its only responsibility is managing the SceneViewExtension via a tshared pointer. It's also declared as a friend class, so the SceneViewExtension can access its private members. This approach might not be to everyone's taste. Please don't hate me. Anyway, during subsystem initialization, I create a new extension and pass a pointer to the subsystem itself. Upon deinitialization, I reset it. Here's the code for drawing the debug data received from the render thread, nothing fancy. And here's the blueprint exposed function used to set the internal texture resolution. And that's it. The subsystem is automatically created by the engine, and so is the SceneViewExtension. We don't need to manually tick or call anything. Each frame it gathers data on the game thread, stores it for render thread access, runs the compute shader, and writes the resulting texture to the scene uniform buffer along with the mapping information. That data can be accessed in HLSL via a .ush or USF file included inside a custom node in a material graph where we call our sampling function. Same result as before, but without relying on an external render target. Now, I'm not entirely sure about the long-term implications of this approach. For example, I know uniform buffers have size limits. So at first, I wondered whether I was even supposed to send a texture or buffer through them. But from what I understand, the uniform buffer doesn't actually store the texture data itself. It stores a sort of reference to the resource, which lives in GPU memory as expected. So this likely increases the uniform buffer size by only a few dozen bytes at most, assuming I'm correct. I could be wrong. Still, even a few dozen bytes might matter. Is it a good idea to add extra data to the scene uniform buffer? Is there a performance cost to bloating it? I honestly don't know. The same question applies to scene view extensions. I assume they come with some overhead. I doubt you're meant to create a large number of them, so I'm not sure whether using them, along with extending the scene uniform buffer, just to implement a small VFX and avoid an external render target, is the best architectural choice. That said, it works, and it feels very powerful, so I wanted to share the technique. Finally, as promised, let's wrap up the video with an overview of the C++ port of my God of War style dual depth system, which originally relied on blueprints and Niagara. I explained it thoroughly in another video, so if you haven't seen that one yet, you might want to check it out for more context. Originally, the system used a blueprint to gather static mesh transforms, as well as skeletal mesh bone transforms in order to pose virtual shapes that were then ray-traced for depth using Niagara simulation stages. The new version is written in C++, and most of it isn't particularly exciting. It also builds directly on everything we've discussed so far in this video, so I'll keep this part brief. I have a subsystem with a few methods for adding and removing static and skeletal meshes. It's essentially a one-to-one port of the blueprint system. Again, all the detailed implementation is covered in the other video. This subsystem manages the lifetime of a scene view extension and passes itself to it. On each tick on the game thread, the scene view extension calls into the subsystem to gather the shape buffer data, fetching shape extents, socket and bone transforms, and so on. At this point, I also retrieve the view location, which is used as the origin for mapping the textures. I also capture additional information like element indices within the shape buffer. In the end, this struct contains all the data required for safe use on the render thread. And this happens in two places, pre-render view family and pre-post process pass. One thing I haven't mentioned yet is that the great advantage of a FSceneViewExtensionBase is that it provides numerous hooks into different stages of the rendering pipeline. Some passes are executed before others, so depending on what you're trying to achieve, and which part of the engine or which render data you need to access, you have to perform your work in the appropriate pass. In pre-post-process pass, I rasterize the ground height because I need to sample the global mesh distance field, and the necessary resources are not yet created when pre-render view family is called. Anyway, I'll keep this part brief since it could easily be a video on its own. First, I create a tconst strided view from the view passed into the function. This allows me to call a useful utility function that returns a pointer to the global distance field parameter data, which I then provide to the rasterization compute shader addPass function. The compute shader itself includes a struct called FGlobalDistanceFieldParameters2. Binding this struct requires a bit of work. So I get the pointer to the FGlobalDistanceFieldParameter data and verify its validity. And essentially, it seems you have to convert from one representation to another, assigning a number of fields along the way, including several values obtained from cvars. And finally, I bind the struct. This enables the inclusion of two specific headers in the compute shader file, which grant access to the distance field sampling function. Note that the sample position must be relative to the camera, aka translated. From there, the shader performs a sphere trace downward to detect the ground and writes the result into a structured buffer, which is then extracted to persist for the next frame. On the following frame, the rest of the magic happens. First, if anything goes wrong, I make sure to send empty data to the scene uniform buffer to prevent issues. Next, I pause all the shapes. This allows to shift some mathematical computations from the game thread to the render thread. Then I fetch the data from the cached render data struct, and I fetch the ground height stored in the persistent structured buffer. After that, I rasterize the shape depth, uploading the paused shapes buffer to the GPU, creating the necessary output buffers, and dispatching the shape rasterization compute shader along with the local to world transform pass. Again, the full details are covered in the other video. Next, I dispatch the dual depth compute shader using another persistent structured buffer, which is then converted into a texture 2D for sampling. Finally, I dispatch the persistent depth compute shader using yet another persistent structured buffer. The result is blurred using a naive iterative separable box blur, and then converted into a texture 2D for sampling as well. Once that's done, I have textures for both the dual depth and the persistent depth, which I expose to all shaders through the scene uniform buffer, declared here and implemented here. I also send debug shape information back to the game thread. With the scene uniform buffer now containing my custom struct, which itself contains pointers to two textures and samplers, as well as mapping data, I can access it directly in shaders. I even have a sample function that recreates what used to rely on a render target, now written in HLSL and sampling the internal texture instead. And that's pretty much it. I went from a system that took several milliseconds on the game thread due to blueprint overhead and Niagara's small CPU cost, to something that runs in roughly 150 microseconds, with some of the workload shifted from the game thread to the render thread. The GPU cost also appears to be lower on average, but that would need to be validated with an algorithm that has a much higher baseline cost. The original implementation was already so inexpensive in Niagara that it's hard to tell whether it's truly worth the effort of moving from a Niagara simulation stage to a pure dispatch approach. That's the end of this long video. Once again, I went down quite the rabbit hole, so I apologize for the delay. This is a topic I've wanted to dive into for a long time, and with virtually no background in programming, let alone GPU programming, it turned out to be much more complex to turn my findings into a clear educational video. My own understanding is still a bit shaky, but I truly did my best. If you notice any mistakes, or if I got something wrong, please feel free to correct me in the comments below. Still, I hope this video will be valuable to many of you. At the very least, I hope it inspires you to have fun experimenting with compute shaders. Anyway, this will most likely be my final video on this YouTube channel, at least for a while. So I also want to say thank you to everyone who has followed along and supported me over the past few years, whether by simply watching the videos, leaving comments, following me on social media, or, of course, supporting me on Patreon, which has genuinely reshaped my life. I'm incredibly grateful to all of you. There's not much more I can say beyond that. Thank you. That's it. Maybe I'll see you here and there on social media, Discords and forums. In the meantime, take care of yourselves. Bye bye.